Alright, time for another DraftPhysics.com video presentation. DebatePhysics.com also. Videos can be found there, selected for their relevance to specific subjects under dispute. And unfortunately, in a dispute, you need to make arguments, and then there needs to be counter arguments that are relevant to the arguments made. And unfortunately, can't make that happen on this internet. Anyway, so physicist Michael, in making a video about 9.8 meters per second squared, or per second, and kind of emphasizing that somehow this is the formula that must be believed, that Newton didn't say 9.8 meters per 1 second, when yes, of course he did. He said 16 feet per second, but whatever. And you don't need to square the seconds. You do have to just understand that you're occurring velocity as something moves. So in gravity, you're losing velocity at a rate, and in gravity, you gain, going with it at a rate. And as you're gaining it, you're able to capitalize on what you've already acquired. It'll keep giving you. Okay, it's the gift that keeps giving when you're falling. And it's the nasty bit that keeps taking when you're going against it. And it's not linear in the sense that the first foot you lose isn't the same as the last foot you lose, so to speak. So I thought I would play this video where he's doing some of the collecting the experimental data for something that's been known for 500 years. Everybody already knows the outcome, so to speak. It's not in dispute at all, but there are features of this experiment, very close to this experiment, little tiny modifications of this experiment that are under dispute. So I just figure I'll go through some of that. So there's a real question about whether momentum is conserved. Now, even though it's supposed to be forever and always, it's apparently not. Now, I would say it is. It's just that the experiments are less than perfect. So there's one experiment that demonstrates something totally, I'd say, just can't be. So you have the same force, okay, same explosion, you could call it, and you have two different experiments, okay, one with one mass objects, one with two mass objects, and somehow, okay, in this experiment, you get 400, let's just say, and 200 as your momentum numbers. Now, at first I didn't realize that the only way you could get these numbers is the speed here has to be exactly the same as the speed here. So somehow this compression, even though this weighs half as much, it's only pushing it at the same speed as pushing the two masses. So the velocity here is the same as the velocity here. Because the only thing that can change these numbers, momentum numbers, is that this has to be going the same speed. So instead of going 1.4, it's going 1. So that's kind of strange. Because we have these other experiments by the Brozo claiming that the same spring, okay, is compression, all right, and you give it a 2 mass and a 1 mass, that somehow the 2 mass goes at, let's say, 2 velocity. And, no, make it 1 just to keep it simple, 1 velocity. And the lighter mass, half as much, doesn't conserve the momentum. The spring doesn't conserve momentum, and it only leaves with 1.4. Now, other experiments, okay, with levers, done by Brozo and me, they basically say that the same spring compression done on a lever, okay, with masses at the appropriate locations to convert the energy appropriately, this goes twice the velocity that this goes. And that's sort of my finding. Also confirms that this appears preliminarily to be twice the velocity, not 1.4 the velocity. Now, it's also a fact that you can make a lever, and you could even have a 4-to-1 relationship. You can put a object 1 unit of distance here, 4 units of distance here. Okay, and it will oscillate perfectly, indicating that, you know, it'll go up and down perfectly. That this object would have, you know, 4 times the velocity of this object, and that momentum is conserved. So then also coupled oscillators. So I've done that experiment. This is essentially a coupled oscillator, it's just a straight bar. It's pretty rigidly coupled. More slightly coupled oscillator with the 2 mass and the 1 mass. And the finding is that yes, this oscillates with twice the displacement that this oscillates with, indicating that you do conserve the momentum. Momentum goes from here, goes back and forth between the two perfectly fine. So we really just don't have any, I mean, I'd say it's semi-clear, but I mean, it's pointing in the direction that momentum is conserved, and we just say this is an aberrant, and other experiments claiming otherwise, or something's broken, something's not working right. You know, it can be the only reasonable conclusion, I'd argue. There's also launching. You know, I think the Gosling guy launched objects and found that he couldn't make the half mass go the appropriate distance. And dropping also somehow the half mass doesn't have the same weight, okay, as it, you know, it should have in terms of dropping these two things in the same distance. But then when he dropped them on clay, they did produce the same weight. You know, the half mass from 4 times the distance did produce the same destruction of a piece of clay. So yeah, so this experiment's all over the place, and we really don't have anything, I would argue, a clear statement. I mean, maybe it's somewhere, maybe somebody could find the quote for me where physicist Michael says exactly what he says springs do. Do they conserve momentum, or do they conserve kinetic energy? Now, it seems to me he is saying that they do conserve kinetic energy, but his own experiment demonstrated that it didn't even, his own experiment confirmed that, you know, again, that instead of it being this 1.4 velocity that would conserve kinetic energy and momentum, well, it can't conserve momentum because 1.4 isn't 2. But we got a different number. I mean, the velocities don't match. The spring in one case was producing the same velocity, only a 1, and in the other case it was producing the 1.4. So yeah, it's confused. So we really just don't know. I mean, what's the simple answer, right? I mean, you have the same spring theoretically to conserve momentum. If I put a half mass on the same spring and I shoot it into gravity, so gravity is going to take its energy away. The fact is this should go 4 times the distance, because it should have twice the velocity, because it only weighs half as much. So that, I would say, is what certainly is the physics I thought was true most of my life. So if it's not true, somebody ought to explain why it's not true. I mean, at least I thought the half velocity thing was pretty much guaranteed. Half the mass, twice the speed. Yeah. But we really don't have that statement. So again, we're just sort of sitting in this, you know, where this is unresolved, and it really should be resolvable. I mean, there should be experiments that just overtly show it. It's just that they're hard to find. I mean, I could go to the Mythbusters one, different experiments that seem to indicate that this is true, that the momentum is conserved, but they're just wherever the videos are, they're not easily accessed because they're not easily properly titled or something. But so far so bad in terms of finding this simple experiment of launching an object with a spring and seeing what it does. Now I could go to maybe I'll do that first. I'll go to a Bruce Yerney video. Okay. It just demonstrates, shit, why don't you do the other experiment? You know, why are you doing this one? Why don't you do the other one? Alright, I'm back, and I'll put this on. And so this is a Bruce Yerney video. It's pretty short, so maybe we'll just kind of bounce through it.
Shani, and today I'd like to look at a descriptive event that's going to involve these two dart guns. Now these guns are identical, except for the color. Now we can start our investigation by comparing two identical darts in these guns, and we should see them move at the same speed.
Now, my wish would be is that obviously just make one of the darts half as massive, cut the end off one, do something to make them half, one weigh twice as much, and then do this experiment and prove that the half as massive dart goes twice as far, because it can't do anything else. Velocity will decide how far it goes. Doesn't really matter about mass, because gravity is the thing pushing them down. They'll all fall at the same rate.
So I'll move them against the wall, I'll fire at the same time.
So fairly good example. I mean, it worked. His angle's a little off here, so he's shooting this one up a little higher, which is, well, not too perfect, but whatever. You get the idea. The velocities are the same. So it'd be really great if he just put a heavier thing in that was exactly twice as heavy, but he's not going to do that.
And we see that they move together.
Now it's time to make a change. I'm going to make one of the darts heavier by adding a heavy steel nut to it.
But he's not going to shoot it sideways. So he's going to shoot it down to demonstrate that, frankly, the lighter dart's going to go further, because it's not going to be slowed down by the slower initial velocity. The initial velocity of the orange thing is going to be very high. Initial velocity of the heavy thing going to be very low. And therefore, one of them is going to fall faster in the gravity because it's already got a velocity that's much higher.
Now, if I were to hold these two guns vertically and fire them towards the ground, which dart do you think would hit the ground first?
The one that isn't going to be slowed down by being much heavier. That's right.
Now, when I ask this question of students or even adults, I'm always surprised by the number of people that have it wrong. So, which dart do you think would hit the ground first?
I hate these test videos. It's like the worst thing on the internet is people trying to teach you something and doing it with quizzes. Fuck you. Especially when they do quizzes where they don't answer the question. That's even worse.
Well, let's try it and see.
Yes, do that. Okay, so that's really fast and I can't see anything. There we go. So obviously the slow one leaves slower. So this really isn't about gravity, it's about which one leaves the gun quicker, and obviously the one that leaves the gun quicker is the one that's going to have a huge advantage, blah, 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 blah. Gravity isn't doing much here. 95% of the velocity that these objects will acquire, because they hit the ground so fast, is going to be the velocity they left the gun with. Gravity is going to almost mean nothing. It's such a minuscule percentage of whatever velocity the objects will have will be created by gravity. They'll land pretty much with the same velocity they would have hit the ground or a wall with, because they're not in the gravity very long.
When I pose this question to my students, I have them make predictions, and then I have somebody try it to see what happens.
Duh. Gee, that's really fascinating. It really isn't. Okay, well, let's just play it through since we're here.
Oh, yeah. I knew it!
We tried it from higher heights,
I don't think I'd have students standing on desks. Seems like a huge liability.
and still got the same results.
Oh,
Now the question is,
See, gravity could only add to the two objects. That's all it can do. It just adds. So one of them will have a little added velocity. That is, the one with the heavy weight on it will actually gain some velocity, where the lighter one will gain almost nothing from gravity because it won't be in it as long. That's the real physics. It's how long you're in the gravity.
why did we get the results that we got? Now the explanation actually starts with Galileo. he first described that light objects and heavy objects will both fall and accelerate towards the ground.
Right, they'll fall at the same rate because they're collecting a different amount of force, because they definitely are different buckets. One of them has more material pieces to collect with. So it's like having a bigger solar panel. You'll collect more photons. So your mass decides how big your solar panel is. And the bigger your solar panel, the more energy you'll collect, and therefore you collect a proportional amount to make you fall at the same rate. So your mass is just saying how big is my collector, and then your mass is saying how much energy, how much stuff do I have to move. So it has a size of the collector is proportional exactly to your mass, and your mass is saying how hard are you to move. How fast can you go with a bit of energy? So obviously the big thing needs more energy. Now obviously when they hit the ground, one of them is going to have a much greater impact than the other, because one of them has more mass moving at the same velocity.
At the same rate. Now Newton in his second law described that if force stays the same, an increase in mass is going to decrease the acceleration. And we can see that.
So if he would have just told us what the mass he added was, how much is that weigh versus the weight of the dart, then we could actually calculate whether this 1.4 thing was true. But because we don't have that number, can't do a damn thing with this experiment. Clearly the heavy dart's going to come out of the gun much, much slower. But we can't tell because we're not given enough information. So, pretty huge difference. So this is like 1/8 of the velocity. So you would argue that this mass is 8 times heavier than the dart. So the steel nut is 8 times heavier than the dart. That would be my guess.
Now when I fire these towards the ground, they're both going to fall and accelerate at the same rate. However, since this dart is lighter, it's going to start off with a higher initial velocity from the gun. So,
a much higher. I mean, it's not like it's a higher. It's like 0 compared to almost anything is, but this is a much higher velocity. So there's a huge difference in the velocity they're going to leave the gun with, and 8 times the difference. So one of them is going 8 times faster to start with, and it just keeps that differential. It's going 8 times faster. So the further away you go, the farther you shoot them, the bigger that difference is going to look, because frankly it's 8 times for every unit of time.
it's going to reach the ground first.
Scientists need go with your video because it makes the science so much more fun. I don't think so. Anyway, all right, so having shown that, which was disappointing for obvious reasons, it could have been nice if he just did why they do this. I'm just going to put an arbitrary mass on something, an ambiguous, erroneous mass. I'm not going to double the mass. No, I'm just going to spit on it and maybe put a little poo on it and make it weigh a little bit more, and I'm not going to tell you how much more it weighs. At least half of the experiments are done that way, where you're just saying, why wouldn't you use 2-to-1 relationships or 3-to-1 or 4-to-1? Why would you complicate things by having something that weighs 4.738 times as much or something? It's just, you're just saying that these people aren't really, they don't do this very often, because if they did very often, they'd figure out, hey, you know what, everything's so much easier if you use nice round figures. If you keep everything, if you round the edges, it makes the whole thing a lot more fun. Alright, I'll be back. Alright, should be back, and this should work. So we'll play this video going through launching a ball and just some explanation of that. And so no data also, but I don't know if it matters in this case, because who cares, because he's not making comparisons between anything.
Okay, here we are doing the vertical marble launch trials. We're going to start with the low speed setting, so this is 1 click. So this is low speed setting, vertical marble launch.
So Noaby, he seems to have this as sort of, it looks like a sophisticated device of some kind for launching things. So it would probably be nice, right, if he tried launching things of different masses, okay, because it's a pretty good spring launcher. So we would argue that somehow this one would probably give somewhat accurate results. That every time he launches he might get the same height for the same mass, and therefore demonstrate this is a pretty reliable device. So it would be really great if they sold the device with little balls that were of different masses but the same size. And then you could do this experiment with different mass balls. But apparently they don't do that. Apparently.
Let's give this a try.
So apparently these Galaxy cameras can do 900 and something, 97 frames to 1,000 frames per second, which is really nice, you know, for whatever, a limited 40 seconds or something. But still, you know, that's pretty convenient. So I really have to try to find a cheaper version of that, but we'll see.
See if we got it.
It is a little bit of a hassle to try to start a recorder and start your experiment at the same time. So that's something I've run into because, you know, I have a camera that can do a lot of images, like maybe 400 per second, but it can only do it for, you know, 6 seconds or something. Well, it's less than that, 3 seconds. So that's quite nice, you know. So this would be the experiment to do. So is to, let's see if we can find something this size that weighs half as much, and you know, that fits in this little device the same way and does everything this does, except it weighs twice as much or it weighs half as much. And let's see if that will launch and show us that for whatever reason, springs don't store momentum. They can't return the momentum that goes in. So whatever momentum goes in isn't the momentum that comes out. Alright, very nice.
So that one looked good. We're going to switch to the high velocity case.
This is all for no good reason. He's just doing it in 2 different cases so he can apply the same math and try to get the same answer using 2 different experiments, essentially, with different numbers. So it really doesn't mean much. I mean, it doesn't, you know, he's not making direct comparisons. He's just using 2 experiments, doing exactly the same mathematics and saying, see, they both come up with the same answer for the thing he's trying to detect, which isn't something that's different between the 2. The thing he's detecting is exactly the same for the 2 things. That is, the force of gravity against the motion.
There we go, and 3. So this is the vertical launch, high speed setting, and let's do 3, 2, 1. See if we got that.
So it does seem to shoot very straight and all these kind of things, which is very nice. 960 frames per second, really great. Timer starts when it reaches 0. I don't know exactly how he does that, but whatever. Very nice. Now assume that he's going to now drop a ball from the same height as this highest height, I think. Okay, so see right here on this chart he could point out that, well, you see this 1/4 of the distance? That's where the ball actually reached half its velocity. So all through this 3/4 of the distance, okay, it only lost half its velocity, and it still had half its velocity way up here, and it doesn't lose the last half until it does this section, which takes the same amount of time as this whole long travel. This little travel takes the same amount of time. I mean, to me, that's a kind of a glaring truth that sticks right out and says, wow, that's really weird. I mean, it's weird that it's not, yeah, it's not linear at all. And, you know, it's telling you something. So, this part, see, very slow movement, very slow acquisition of distance. And then it goes faster and faster. As it goes faster, it covers more distance. It just sort of makes sense, though, when you think about it. So it's going to go half the velocity right here. So as it's falling, half the velocity. It's going half the velocity right here. Okay. And it's going to gain only another half through all of this distance. It's actually a little more than half at that point, but whatever. And unfortunately, the camera can only do 960 for a brief number of seconds.
All right, we'll go with that one. In 3, 2.
So he's dropping it from a little higher, so I thought it would be better to drop it from exactly the same height, and then you would know better. You know, you can make a comparison between those two drop times and say, look, see, it doesn't matter whether I drop it or I launch it. It falls the same. Not that that is under dispute either.
1.
So right about there, half the speed. So it's going as half of the total velocity it's going to acquire. It's already got half of it right there. And that whole other distance is just going to give it one more unit of 1/2 the velocity. So 9.8 meters. So let's just say this was a meter. I mean, this was 9.8 meters long. So let's just say this is a shrunken version. Then yes, in the 9.8 unit here, okay, that took 1 second. And then you'd go all this distance, so it's going to be 1 second also. So it did this in 1 second, and then it's going to do this whole distance in 1 second. And, you know, that's a glaring observation, in my opinion. Just tells you, obviously, that it's just 9.8 for here, 9.8 for here. You only got 2 units of force. You only have 2 units of energy. You only weigh twice as much. When you hit the ground, you're just going to weigh the amount of force you've acquired, okay? And so if I was to drop it from one distance, you know, 9.8, and then compare it to this 4 units of distance, I'm going to just double the weight. So even though I'm dropping it from 4 times the height, I'm only going to get twice as much weight, which is really telling you, isn't that a glaring statement that twice the weight, twice the energy? I mean, the weight is what your impact is. It's basically telling you how much force are you applying. How could it be 4 units of force when it's only 2 units of weight?
Okay, I think we're good for this.
All right, so unfortunately they won't directly interact with this video. So I made this video pointing out these arguments, and none of these arguments will be directly argued. So even though these are important points, they won't explain how they're not important points. The fact that you're going half the velocity, only traveling 1/4 of the distance, I say it's an important feature. It's a glaring fact that's been revealed to you. Same with rolling. You roll anything across a surface, anything, it does the same thing in gravity. So if you're rolling in gravity, not in space somewhere or something, but you roll something in gravity here on Earth, not on the moon, well, even on the moon, frankly, the same theory applies in the sense that it's just going to change at a different rate, but it'll be the same proportions. and it's going to do this, it's going to take your velocity in the same mechanism. So you're going to go half your speed after you traveled 3/4 of the distance of the total until it stops. So if you just roll something and watch it stop, you can say 3/4 of the track, that's where it's going half the speed. It doesn't matter, how little you roll it or how much you roll it. It's always got that ratio of 1, 3, 5, 7. All right. So yeah, I've done my part here. Computer's a little buggy. Anyway, so that's enough of a video and such, I think. I was going to talk about photons this morning, but I'll save that for later and such. So till the next time, blah 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 blah.